All right, we have to figure out the average acceleration on a strange interval for an object with a given position function. So we are given a position function. So average acceleration is going to be the change in velocity over the change in time. Because dividing velocity by time gives you an acceleration label. Since it's not an instant acceleration, we're not going to go down to the second derivative. We're going to go to the first derivative. The change in p prime is the same as the change in v. I guess it's not really p prime, it's x prime. They call this x of t, whatever. We're going to get the derivative, find out how much it changed, and divide it by e squared minus e, because that's a number you see a lot. Okay, so we're going to need x prime. Oh, there it is. Yeah, they always put that in. The natural log of t squared. So to get the derivative here, we're going to need to do u prime over u, but our u in this case already has an ln in it. So I'm going to put ln t squared in the very bottom of this fraction because that is the quantity that we're taking the natural log of. So the tricky part then is figuring out what's the numerator. So this thing in the box, I need the derivative of the thing that is in the box. And maybe before I even do that, I'm going to call this 2 ln t. I'm going to bring the 2 out front using log properties, because that's going to be easier to differentiate. So if I have to get the derivative of this, I can pull the 2 and just differentiate ln t. That's going to give me 1 over t. So to clean this up a little bit, I've got 2 over t in the numerator, and heck, I could even put this 2 out front here, couldn't I? I'm going to do that. I got 2 ln t in the bottom. I would just say put this t in the bottom. If you don't believe me, think of it this way. This is 2 ln t over 1. So now I'm dividing fractions, kind of. So I'm going to do top fraction times reciprocal of bottom fraction. And either way, the t ends up being in the bottom. Quick way would just be to say, if it's in the denominator of the top fraction, then it's really in the denominator overall. But this is why. So the 2's cancel out. I hate saying that. We've got 1 over t ln t for our derivative. So that is x prime. That is our velocity function. So I've got to do velocity at e squared minus velocity at e. That's going to give me the change in velocity. And then I'm going to do e squared minus e to get the change in time. E squared plugged into this velocity function is 1 over e squared ln e squared. And plugging in e gives me 1 over e ln e over e squared minus e. Natural log of e squared is just going to be 2, because if v2 is going to come down, natural log of e is 1. So this fraction is 1 over 2e squared. In this fraction, ln of e is 1, so this fraction is 1 over e. I'm really just doing algebra at this point. I got a kind of a complex fraction here. I'm going to get a common denominator up here. So my common denominator is going to be 2e squared, which means this denominator needs a 2 and another e. So I'm going to put that in on the top and on the bottom. So now my new numerator is 1 minus 2e over the common denominator 2e squared. And I'm going to multiply that by the reciprocal down here, which is 1 over e squared minus e. So I've got 1 minus 2e up top when I multiply across the top. On the bottom, I've got, gosh, will any of this factor? I've got 2e to the 4th minus 2e to the 3rd. I guess I could pull out a 2e e to the third, I'd get e minus 1. That doesn't do me any good. This is fine. It's ugly and messy, but it's a good algebra review. All right, we want to differentiate this fraction. Now, before today, we would have had to have used, I guess, overall quotient rule on it. And in doing quotient rule, we would have had a product rule to get the derivative of the top. I'm going to go add a little commentary here. I don't want to do that. It would be a mess. So option 2, that's the new stuff. We're going to use a technique called log differentiation. And all log differentiation is first applying ln to both sides. That's an Algebra 2 thing. Then applying log properties to both sides, which is an Algebra 2 thing. And then finally doing the calculus, then doing the actual differentiation. So I'm going to say, I'm going to call this function, this is y. So if I take the natural log of y, I also get the natural log of, I'm going to call it x plus 4 to the half. I also get natural log of the right side. Or better yet, I'm going to do log properties now. I'm going to split this up into 1, 2, 3 easy payments. Actually, no, 3 pieces. Natural log of x, because the x is in top, it generates a positive natural log term, plus natural log of this thing, and I could put the 1/2 out front, because when you have natural log of something to a power, the power can be written as a coefficient. See, that could also be put back up here, and you'd have what you originally had written here. Then I'm going to need a negative term because the final quantity is in the denominator. That generates a negative log term. So I have done 0 calculus so far. This is all just applying natural log to both sides and using the properties. Now I'm going to do the calculus. I'm going to differentiate every term, including the one that everyone forgets. This is not going to be y prime. It's not y equals, it's ln y. So when I differentiate it, I'm going to get the derivative of y, not 1, but y prime, over y. So our u prime over u in this case is literally y prime over y. U prime over u here is 1 over x, because the derivative of x with respect to x is in fact 1. For the next term, the 1/2 can be kept as a constant, and we're just going to differentiate the variable portion. Derivative of x plus 4 is simply 1 over x plus 4. So our u prime is 1 over u is the original quantity. Same situation at the end. The derivative of the quantity is 1. The quantity itself is x plus 2. So to get the y by to get the y prime by itself, I do need to multiply both sides by y to get rid of it from the left. So I get y prime equals all this garbage times y. And really, since I have an expression for y at the beginning, I really should substitute that in, because y was explicitly written at the top, so there's no excuse for not writing it explicitly at the end. So I'm taking the y out and putting in what y is. So everything now for your answers in terms of x. They want us again to use log differentiation on this. If we were going to differentiate this otherwise, we'd have to use product rule, but with like 2 parts. So we'd have 3 terms in our answer, and each term would be long, and yeah. So we're going to use log differentiation. I'm going to put ln in on the left and ln in on the right. And that'll allow me to apply log properties to the left side. So ln of x squared could be written as 2 ln x. That generates a positive term. Plus, my next term will also be positive. I'm going to have ln of cotangent x plus I'm going to have ln of cosine x. Since these three things are all being multiplied, they all generate positive natural log terms when I apply log properties. When I differentiate, again, ln y does not become y prime. It becomes y prime over y. Derivative of this term, the 2 can stay. Derivative of ln x is 1 over x. Here we need derivative of cotangent over cotangent. Not a huge fan of dealing with derivative of cotangent. So you know what I'm going to do? I mean, I could look it up. I frankly don't remember it. I could figure it out. But I'm going to write this as ln. I know cotangent is cosine over sine. So I'm going to split this into 2 terms. Since it's a fraction, the positive part gives me a positive log term, and the denominator part gives me a negative log term. And what I've got now is 2 ln cosine x terms. So maybe I'll just rewrite this. I got 2 ln x, already taken care of that. Then I get 2 ln cosine x's, and then minus an ln of sine x. So I've differentiated this one already. Now I'm going to differentiate this one. I'm going to keep the 2, and then differentiating cosine, natural log cosine, gives me u prime. So derivative of cosine is negative sine over u, which is just cosine. Differentiating sine, I got to do u prime over u. So u prime, derivative of sine is cosine over u, which is sine. So I'm going to have something here times y, because I'm going to multiply this y onto the other side. So I've got a 2 over x here. I've got, this is a negative something, negative 2 something. Sine over cosine is tangent. And then this thing, cosine over sine, is cotangent. And then since I have y explicitly written in the beginning, I can put in what y is explicitly at the end. So the 2 over x minus 2 tangent x minus cotangent x all stays, and then I multiply on all this stuff. X squared, cotangent x, cosine x. Ugly as it is, I'm not going to be judgmental about it. It has every right to exist.